So the aim of this podcast is to give you the opportunity to practice the study of circular motion. So what I'd like you to do is to consider the following trajectory. R is a position as a function of time t, and I and j are the unit vectors in the x and in the y directions respectively. All distances are measured in meters, time is measured in seconds. So what I would like you to do is to write this down and then on paper with a pen try to draw the trajectory here, mark the radius of the orbit, to work out what the period, frequency and angular frequency of the orbit are, to calculate the velocity of the particle following this trajectory and to work out what its speed is, to show that the velocity vector and the position vector are orthogonal, they're at right angles to each other, and then finally to calculate the acceleration vector and to see how its direction is related to the position vector and the velocity vector. So I'd suggest that you pause and then write this down, attempt it, and then afterwards you can carry on and look at the answers. So welcome back. The first part of the answer is to consider the trajectory given here, and then what we want to do is to see that this describes a circle, and the easiest thing perhaps is to recall the equation of a circle, that x squared plus y squared is r squared, where r is the radius. This is of course for a circle centered at the origin, and x can be read off from here. It is 6 cos 3t, and y is 6 sine 3t. Again, it can be read off from here. So x squared plus y squared, they've both got a factor of 6, so we're going to get 6 squared from x squared and 6 squared from y squared times cos squared of 3t plus sine squared of 3t. And then we just recall that the cosine of an angle squared plus the sine of the same angle squared always adds to 1. So that's a very useful identity. So this is 1, and we see that x squared plus y squared is 6 squared. This means it's independent of time, and it is indeed following a circle, and the radius is 6 meters because this side is 6 squared. That's a length squared, that's a length squared, and the radius is 6 meters. So that's the circle that our particle is going around. A different way of calculating this would be to use vectors. We have the position vector given here, and if we take the scalar product of a vector with itself, we get the square of the magnitude of that vector. So the scalar product of r with itself is written here, and we just have to multiply the coefficient in the I direction with itself and add the coefficient in the j direction multiplied by itself. So we get 6 cos 3t times 6 cos 3t, and I've dropped a factor of 2 there, a squared factor there, so that's cos squared. And so we have here 6 cos squared 3t plus 6 squared sine squared 3t. 6 squared is a common factor, we pull it out, and again we recognize the same identity. So we see that the magnitude of the position vector squared is 6 squared, so r, the magnitude of the position vector, is simply given by the square root of 6 squared, so it's again 6 meters, and that's just what we would expect from the other way of approaching it. So we're going around a circle, it's centered at the origin, and its radius is 6 meters. The next questions are about how rapidly it is going around that circle. So in this part, what we want to do is to calculate the period of an oscillation, the frequency, that's the number of oscillations per second, and the angular frequency. So here is our equation for the position. It involves the trigonometric functions cosine and sine, and they have a periodicity property that if you increase whatever their argument is by 2 pi, you get back to where you started. So if we say 3t, that's the value here, increases by 2 pi, then this and this will be unchanged, and we're going to say that one period has passed because 2 pi is the smallest value after which you get back to where you started. So 4 pi, 6 pi, 8 pi, etc. would all be the same as where you'd started, but that would be 2 periods, 3 periods, etc. So if 3t goes to 3t plus 2 pi, we've had a period of time has passed, and that means that t has increased, little t, from whatever its value was to t plus capital T, the period. So 3t plus capital T is equal to, then on this side, 3t plus 2 pi. The 3t's, little t's, will cancel here and here. You see they're the same, so we can cancel those. That goes with this, and what we are left with is that 3 times the period is 2 pi, and dividing both sides by 3, we see the period is 2 pi over 3 seconds. And a very simple check, and you could have just used this to calculate it, would be to say at what value of the time the smallest value of the time, am I going to get back to the position at t is 0? And I'd encourage you to make that check and see that you get this same value. So now let's think about the frequency. Frequency is the number of oscillations per second. The period is the time taken in seconds for an oscillation. So let's say, for example, that the period is 1/10 of a second. What that means is that in 1 second you can fit in 10 oscillations. The frequency would then be 10 per second, or 10 hertz. So frequency is given by the reciprocal of the period. This is the period, and its reciprocal is just 3 over 2 pi. And all I've used here is that if you divide 1 by a fraction, that's the same as multiplying 1 by the reciprocal of that fraction. So I just put the numerator on the bottom and the denominator on the top, as I did here. So the frequency is 3 over 2 pi per second, or 3 over 2 pi hertz. What about the angular frequency, which we normally call omega? Well, f, the frequency, is the number of full orbits per second, and we can say that's 2 pi radians per second, because going all the way around the circle is going through 2 pi radians. And omega is the number of times we go through 1 radian per second. So omega is 2 pi times the frequency, because the frequency is the number of times we go through 2 pi radians per second. So to get the number of times we go through 1 radian per second, we just take the frequency and multiply it by 2 pi. So 2 pi times 3 over 2 pi, the 2 pi's will cancel and we'll be left with 3 radians per second. So that will be our angular frequency. And it's useful perhaps here just to remember the two different ways that we often write such things. We can say that the position vector, if we have circular motion, is the radius times something like the cosine of omega ti plus r sine omega tj, and we see here that this is falling into exactly that form, because here we have 3 and here we've seen that omega is 3, and r on the outside the radius is 6. Another way of writing this, but it involves extra 2 pi factors, so it's not as simple as writing this, is to say that the position vector is the radius times the cosine times 2 pi times the frequency times t in the I direction, plus r, and then the sine 2 pi times the frequency of t times j, the unit vector in the j direction. And if we do that, what we see is that if t is 1 over f, then they will cancel if t is 1 over f, so after a period has passed, and we'll see that r of t is r cos of 2 pi plus r sine of 2 pi with i's and j's, and cosine of 2 pi is the same as the cosine of naught, sine of 2 pi is the same as the sine of naught, and so we see we'd have exactly the same form for r at the period as we would have at r of naught, which is what we would expect, because at the time when one period has passed, we've gone all the way around the circle, and we should get the same position as you would start with when the time was 0. Okay, let's move on to the next part. So in the next part we're asked to calculate the velocity and speed, and velocity is given by the derivative of the position vector with respect to time. And if you are differentiating a vector like this, where t is here and here in the coefficients, then I and j are constants, and all we do is we differentiate the coefficients here. So to differentiate 6 cos of 3t, the 6 is a constant, it just multiplies everything here. We can take the derivative through it. The derivative of cosine is minus sine, and then the argument is unchanged, so we have minus and sine of 3t. And then from the chain rule of differentiation, we multiply by the derivative of the argument, so the derivative of 3t with respect to t, and that just gives us a factor of 3. So the 3 multiplies the 6, and we have 18. So a minus sign from the derivative of cosine being minus sine. 3 sixes are 18, following from the chain rule, and the argument is unchanged. And in a similar way here we get plus 18 times the cosine of 3t, and the units are meters per second. Meters per second. So that's the velocity vector, and it clearly changes with time. The values of the sine and the cosine functions change. What about the speed? Well, the speed of the particle can be calculated by taking the scalar product of the velocity with itself and taking the square root of it. This is the magnitude or the size of the velocity vector. So to take the scalar product of this with itself, we just multiply this coefficient by itself, and if it's negative and we square it, it's going to become positive. We're going to get 18 squared times the sine squared of 3t, and then we add the square of the second coefficient, so that's going to be 18 squared times the cosine squared of 3t. So 18 squared is a common factor, we could pull it out in front, and then we're going to have the square root of 18 squared times sine squared plus cos squared. So the square root of the 18 squared is 18, and the square root of sine squared plus cos squared, well, sine squared plus cos squared is 1, so we've got the square root of 1, and that is of course just 1. So the speed is 18 meters per second, and it's important to recognize that this does not depend upon the time. It is a constant speed, although the velocity, the direction of motion, is changing. So that's a very important result, and it's worth a check. And a simple check to make would be the following. The average speed over a full cycle going all the way around the circle is going to be the distance travelled, the circumference of the circle, 2 pi r, divided by the time taken, and that is the period. Now we know the radius and we know the period, so we could just substitute their values into this to work out the average speed over the full cycle. And because the speed is constant, the average speed is going to be that constant speed. So the radius we've said is 6 meters, and the period we have said is 2 pi over 3 seconds. So the speed is 2 pi r, 2 pi times 6, divided by 2 pi over 3. So here we are dividing by a fraction, so that's the same as multiplying by the inverse fraction. That means that the 3 goes to the top and the 2 pi stays on the bottom. The 2 pi factors will cancel each other, and we will get 3 times 6, 3 sixes are 18, so we obtain that the speed, the average speed going around the circle, is 18 meters per second, exactly what we obtained a moment ago using vectors. This is a more fundamental calculation. This relies upon the fact that we have seen that the speed is constant, and it is really a check of our results. So with that, I'll move on to the next part. So here what I want to do is to show that the position and velocity vectors are orthogonal. And to do that, let's just recall a few things. So if two vectors are orthogonal, if they're at right angles, their scalar product vanishes. So let's just, to see that, remember the basic result, that if we have two vectors and we take their scalar product of A and B, then the scalar result that we're going to get is the magnitude of A times the magnitude of B times the cosine of the angle between them. And if vectors are right angles, then we get that this vanishes because the cosine of pi over 2, or the cosine of 19 degrees, is 0. So let's see what happens here. This is the position vector. This is the velocity vector that we just calculated on the previous slide. And if we take their scalar product, that can be done by multiplying this coefficient by this coefficient and adding to it this coefficient multiplied by this coefficient. So here we have 6 cos 3t multiplied by minus, so I'm going to put brackets around it, 18 times sine of 3t, plus, and then the bits from the j direction are 6 sine 3t multiplied by 18 cos of 3t. So in both terms there is a factor of 6 and a factor of 18. There is a cosine of 3t and a sine of 3t, here in the opposite order, but it doesn't matter because these are just now scalars that we're multiplying together. So we have minus 6 times 18 times the cosine of 3t times the sine of 3t plus 6 times 18 times the sine of 3t times the cosine of 3t. And we see that this and this are exactly the same, but there is a minus sign, a relative sign, so they will therefore cancel each other and the scalar product vanishes. That tells you that the position vector and the velocity vector are at right angles. They are orthogonal. So with that, we'll move on to the next part. So we've calculated from the given position vector the velocity vector, and we now want to find the acceleration vector. The acceleration vector is the second derivative of position with respect to time, or if you wish, it is the derivative of the first derivative, and the first derivative is the velocity. So you can obtain the acceleration vector by differentiating the velocity vector once. So we differentiated this once to get this, we differentiate this again once more to get the acceleration vector. So it's the derivative with respect to time of this, which I've just written out here. Again, minus 18 is a constant, we can pull it through. The derivative of sine is cosine, so that becomes cosine, the argument is not changed. And then from the chain rule, we multiply by the derivative of the argument, and the derivative of 3t with respect to t is 3. So we're going to get a factor of 3. 3/18 is 54. Over here, when we differentiate this, we're going to get 18, and then the derivative of the cosine is minus, so we put a minus sign there, times, and then it's going to become sine. The derivative of cosine is minus sine. The argument is unchanged, and then we multiply by the derivative of 3t with respect to t, so that's a factor of 3 again, and again 3/18 are 54. So this is our result for the acceleration vector, and the units are meters per second, so it's meters per second squared. Now, if we look at the acceleration vector and the position vector, well, we hopefully notice that they are closely related. There is a minus sign here and here, but otherwise we have got in the I direction the cosine of 3t times a number, and in the j direction the sine of 3t times the same number. And that's exactly the structure that we got here, but with a different number. And if you think about it, 54 is given by 6 nines, so the acceleration vector is minus, because of these two minus signs, 9 times the position vector. So that is our acceleration. So the acceleration is in the same direction as the position vector, except for the fact that there is a minus sign. So the minus sign means it's actually in exactly the opposite direction to the position vector, and we can say that they are anti-parallel. So the picture that we are getting out of all of this is we are considering circular motion centered at the origin. The radius is 6 meters. The position vector is in this direction. The velocity vector is orthogonal to it, it's at right angles, and the acceleration vector is back towards the origin. And that makes sense because acceleration is proportional to force through F is ma, and the force vector for circular motion is pulling you always, accelerating you always towards the origin. And in this picture here I've drawn that we have anti-clockwise motion, and the easy way to verify that that's true is just to see what's happening when t is 0. At t is 0, our position vector up here is 6 times the cosine of 0, which is 1, so it's 6 here overall, I, plus 0, because sine of 0 vanishes. So the position vector at t is 0 is 6i. That means that it is on the x-axis here at a distance 6 meters away from the origin. And the velocity vector at t is 0, we just go back to here, put t is 0 in, that vanishes because sine of 0 vanishes, and here we have 18 times the cosine of 0, which is 1, so we have 18j. That is positive, so the velocity at t is 0 is in that direction. So what we see is that the particle is going anti-clockwise around the circle, and that's why I've drawn the velocity vector in that direction. And with that, I'll stop this podcast.